Hope that this session will give you more contextual understanding about determining the associated cost of the minimum duration of a project in network analysis. This presentation is a continuation of previous videos as a part of network analysis. This relatively covers the main sections of minimum duration and its optimum cost in time analysis. They are an introduction, minimum duration and critical path, cost estimate for minimum duration, and Tactic 1 of Approach 1 with an example. The links for the previous related videos are also given below for your reference. Introduction. This section of network analysis explores the determination of the minimum duration of a project and its crashed cost in relation to the crashed cost of relevant activities and other cost or income. In this section, the project is primarily targeted to complete in its crashed duration, not the cost. However, this part illustrates how the minimum duration and its efficient, optimal, associated cost can be determined with relevant adjustments in relation to crashed duration and cost of an activity. This presentation is organized with minimum duration and critical path and cost estimation for minimum duration. The term minimum duration and associated cost is first introduced by Lucy, 1979. However, this methodology to derive the solution is first introduced by Somathambi Senthilnathan in 1990, while he was serving as an academic at Eastern University, Sri Lanka. Based on the crashed duration of a project, its potential minimum duration can be determined. However, its associated optimized cost can be determined with two approaches consisting of three tactics. Approach 1 consists of two tactics, Tactic 1 and Tactic 2, and Approach 2 has the third tactic, known as Tactic 3. In this presentation, Tactic 1 of Approach 1 is explained with an example to determine the minimum duration and its associated cost. Tactic 2 of Approach 1 and Tactic 3 of Approach 2 are to be illustrated in the next videos. Minimum duration and critical path. Crashed duration is simply the minimum duration in project implementation. It is impossible to complete a project in less than its deterministic crashed duration. Thus, crashed duration is known as the project minimum duration since the crashed duration is the least possible completion duration of the project. The activities that constitute the minimum duration are known as the critical activities, and stating them in the order of their completion is the critical path of the minimum duration. To determine minimum duration of a project, it is important to draw the project network with crashed duration of activities and decide the durations of EST and LFT for every event in the project network diagram. The cost estimation also takes place based on these arrangements of determining the minimum duration. Cost estimation for minimum duration. As indicated earlier, there are two approaches to determine the optimum cost of the minimum duration of a project. In these two approaches, three tactics can be used. Approach 1 consists of two tactics, known as Tactic 1 and Tactic 2, and Approach 2 has the third tactic, known as Tactic 3. In this presentation, Approach 1 with the first, Tactic 1, is explained with an example to determine minimum duration and its associated cost. Approach 1 indicates reducing unnecessary crashed costs from total crashed cost of activities. This implies that the additional costs that are incurred unnecessarily by crashing durations of activities need to be reduced from total crashed cost of a project to determine efficient, optimal, associated cost of the minimum duration of the project. This approach basically considers total crashed cost of a project and consists of two tactics. Tactic 1 of Approach 1. Using the network diagram and its critical path with crash durations of activities in a project, the associated cost of the minimum duration of the project can be determined by adjusting unnecessary crash durations of the non-critical activities and their related costs against total crashed cost of the project. In this context, cost slopes of the non-critical activities are considered for these adjustments. Tactic 2 of Approach 1. Note that this Tactic 2 will be illustrated in the next video. Tactic 2 of Approach 1 implies that the efficient associated cost of the minimum duration of a project is determined in consideration of a. the network drawn on the crashed duration of activities, and b. the combinations of non-critical activities in the network and their relative sums of cost slopes, in view of adjusting for unnecessary crash of activity durations. In the above two tactics, Tactic 2 always results in efficient determination of associated cost of minimum duration of a project, and Tactic 1 can be applicable only for the projects with certain information. Though there is no clear indication about the projects, where both the tactics can provide similar results as consistent as possible. Thus, in determining the associated cost of minimum duration of the project, Tactic 2 plays a constructive role as a significant approach with a series of processes. However, for giving you some preliminary explanation about the adjustments to be made, the following illustration can provide a clear understanding with an example of employing Tactic 1. Now, we move on to illustrate the method of applying Tactic 1 of Approach 1, with an example. Relatively, the information of a project to be implemented by ABC Company is given in a table here. The activities is identified from A to E, and their preceding activities, normal and crashed durations, normal and crashed costs, and cost slopes are given in this table. Using the information, you can determine the minimum duration and its associated cost of the project. Basically, application of tactics begins with the network diagram of a project that is associated with its normal duration and normal cost. Hence, the network diagram of the project with normal duration is presented here, as per the given information. This network diagram indicates that normal duration and normal cost of the project are 14 days and $1,250, respectively. The critical path of the project consists of the activities A, C, and E, as shown by the thickest arrows in the diagram. To determine the minimum duration of the project, draw the network diagram by applying the crash durations of the activities instead of their normal duration, as shown here. The new network diagram with the crash duration indicates that minimum duration of the project is 10 days, and its new critical path by crashing the durations of activities is A and D, as shown by the thickest arrow in the diagram. In consideration of crash duration-based diagram and the cost slopes of activities, the following steps needs to be implemented for determining the associated cost of minimum duration. Step 1 is determining the non-critical activities. Notably, in the crash duration-based network, activities B, C, and E are the non-critical activities, and activities A and D are the critical activities. Hence, the non-critical activities B, C, and E need to be considered to determine the associated and optimal cost of minimum duration of the project. In Step 2, consider the cost slopes of non-critical activities and their respective saved duration by crashing. Accordingly, for activity B, the saved duration is 3 days and its cost slope is $70. For activity C, the saved duration is 2 days and its cost slope is $50. And for activity E, the saved duration is 2 days and its cost slope is $200. For an activity, the duration saved is the difference between its crash duration and its normal duration, and cost slope is available in the initial information table, and they are taken into consideration at this point. Note that if the cost slope of an activity is not given, you should determine it. The cost slope of an activity is the difference of crashed cost and normal cost, divided by its number of saved duration. In Step 3, among the non-critical activities, consider the activity with the highest cost slope. Then, its duration to be saved can be adjusted or reduced without affecting the minimum duration of the project. In the example, Activity E comparatively has the highest cost slope of $200 with 2 days saved. It is notable that there are 3 paths for completing the project. Path P1 consists of activities A, D with completion duration of 10 days. This is the identified critical path with the crashed durations of activities. Path P2 consists of activities A, C, E with completion duration of 9 days. And Path P3 consists of activities B, E with completion duration of 8 days. It is also notable that the paths P2 and P3 has activity E on them with the completion duration of 9 and 8 days, respectively. Now, consider the highest duration path, in this case P2 of 9 days. This highest duration of path P2 with 9 days of completion duration needs to be compared with the minimum duration of the project's critical path, that is 10 days of activities A and D. The difference between them, that is 10 days minus 9 days equals to 1, and this needs to be compared with the duration to be saved for the activity. In this case, activity E has 2 days saved. In this context, the minimum of them should be used to adjust the crashed duration of the considered activity, here activity E. Now compare difference of 1 day and duration to be saved of the activity E, that is 2 days, and consider the minimum of them, that is between 1 day and 2 days. This minimum of 1 day of them needs to be considered for adding to the minimum crash duration of 3 days of activity E, to have its adjusted duration of 4 days, that is resulting from 1 plus 3. After performing this adjustment that is adding 1 day to crash duration 3 of activity E, path P2, with activities A, C, E, now become one of the critical paths of the minimum project duration of 10 days. The network diagram with this adjustment is shown here. It is notable here that, initially, activity C has not been a critical activity, and now with the adjustment in duration of activity E, has made activity C as a critical activity of path P2 with its crash duration of 3 days. Now we have to move into Step 4. That is, the cost of the adjustment made in Step 3 needs to be adjusted with the total crashed cost of the project. When there is a reduction of 1 day in saved duration of 2 days of activity E, the crashed cost for the adjusted duration equaling to 1 times $200 equals to $200, for activity E, has to be removed from the total crashed cost $2,100 of the project. This can result in $1,900 as the adjusted cost of the minimum duration. This is consistent with the adjustment made in the duration of activity E. Now apply Step 5, where consider the new network diagram and respective cost, with the adjustments made through Steps 3 and 4, and go back to Step 2. Follow Steps 2 to 5 until a point where no activity can be adjusted in crash duration, for saving cost. Among the non-critical activities considered in Step 2, it is important to consider in Step 5 the activities, other than the activities considered in Steps 3 and 4. In this example, the non-critical activities initially considered in Step 2 are B, C, and E. Among them, activity E is only adjusted in Steps 3 and 4. Therefore, other non-critical activities B and C need to be considered, if possible, for further adjustment, and go to Step 2. It is important to go back to Step 2 with the latest results after the adjustments made. In this example, for crash duration, path P2 with activities A, C, E was initially of 9 days. Now, after the crashing adjustment of 1 day for activity E, path P2 with activities A, C, E is altered to 10 days of duration for completion, and the path P2 with activities A, C, E has become another critical path for the crash duration of 10 days as the minimum project completion time. Hence, this implies that only activity B of path P3 is the non-critical activity, while going back to Step 2. According to Step 3, the crashed and saved durations of activity B are 5 and 3 days respectively. After the adjustment made in the crashed duration of activity E, it is notable that the completion duration of path P3 is increased from 8 to 9 days. Therefore, it is possible to adjust 1 day from saved duration of activity B to make completion duration of path P3 to 10 days as to be equal to other paths P1 and P2, which are the latest critical paths of the project for minimum duration. With all these repeated adjustments from steps 1 to 5, the final network diagram can be present as shown here. Now, Step 4 indicates that the cost slope $70 of 1 day adjustment, which is made in Step 3 for activity B, should be deducted from the late's total crashed cost $1,900. This implies that this 1 day adjustment, from 3 days saved, of activity B, leads to a saving of additional cost of $70. And this saving $70 should be adjusted with the latest crashed cost of $1,900. Therefore, after this adjustment made in the duration of activity B, the latest associated cost of the minimum duration of 10 days of the project is $1,900 minus $70 equals to $1,830. Beyond these adjustments, no adjustment in duration can be made in any of the activities to avoid additional cost for crashing and to maintain the minimum duration of the project. Hence, according to Tactic 1 in Approach 1, the associated optimal cost of minimum duration of the project is $1,830. It is also necessary to indicate that this Tactic 1 of Approach 1 is only useful for considerably small projects with less activities. The purpose of this explanation is to demonstrate how the adjustments in the crashed cost of a project can be made in prime consideration of minimum duration. However, Tactic 2 of Approach 1 is technically an improved version, which is mostly useful to determine the associated optimal cost of the minimum duration of a project. Hence, Tactic 2 of Approach 1 will be illustrated in the next video. Thank you for watching this video. If you find this video is useful, you may share it with your friends, colleagues, and/or mates. If you need more clarification, you may leave a comment about your thoughts. Your valuable comments can make me produce other related videos meaningfully, with your support. Thank you in advance for your comments to be made. You may watch other relevant previous videos if they are useful to you.